Recording is rolling. Today is Tuesday, August 23rd. So here's the assignment I have for you guys. Wanted to get going far enough where I can make a pretty good estimate of what we're going to do and get a pretty good due date for you guys. So here's what we got going on. I gave you guys a couple of pages on your desk. One page you have looks like this. It has a bunch of tables on it. These are a bunch of linear motion questions. Actually, this is every category of linear motion question that you could be asked. I'll show you guys why that is. You guys can do some of these later. On the back side of that page are 20 conceptual questions. So if you have a really good core understanding of how linear motion works, and all things are doing, it's just possibly moving forward, maybe forward and backward, down, up and down. Right? And we're just talking about motion in a straight line, right? Things could be speeding up or slowing down, but you guys did that in your lab yesterday with the car. Right? If you have a really good core understanding of how this linear motion works, then I think you should be pretty good at these. So I do want to take you guys through these questions too. I think we should have time because we got, of course, like 3 classes worth yesterday and today. So we might do a Kahoot version of those sometime around. Okay? But this page here, these are your chapter 2 questions from your textbook, your college physics textbook. So the PDFs for your textbook are posted online, so you can access the text material. I went through and picked my favorite questions, so there's a lot more questions up there too. So these are the ones that I'm assigning to you guys that I'm going to pick up Friday, September 2nd, and I'll go over some of the ones that aren't listed here, and maybe a couple of these too, maybe a couple of the more challenging ones. Aside from that, you guys also have an AP classroom progress check open for Unit 1. Unit 1 is kinematic motion, which is linear motion, but also some projectiles. So I want to put that far enough into the future where I can at least touch on projectiles before you guys tackle some of these questions. So that there has been open for I think about a week now. Because you wanted to see preview before. Thank you. Here, let me do this. I'm gonna see. Yeah, I'm gonna go ahead and switch my screen over. Get this connected. Okay, connect. Let's try this again. All right, present screens here. All right, here we go. So let's pull it up. This is what the progress check looks like for AP Classroom. Okay, so that is up there, assigned, ready to go. And happy for well, till that due date.
How long would that take
September.
us to finish?
It's only about like 15 or 20 questions, so they're all multiple choice questions. They were okay. Yeah, here's the I'm glad that's about these progress checks. Okay, here's the deal with the progress checks. They're usually about 20 questions, plus or minus a question or two. Now, these are questions that, okay, because they're multiple choice and they're online, you could, don't do this. I've had students do this in the past, and it's always a terrible plan to just cut corners and go through and either just like Christmas tree it, or say, well, it's on the internet. Lots of other students are doing this, and like find the answer somewhere on the internet and then just like plug those in. Right? What you really want to do with these questions is think very deeply about every single question. If you can't solve it, then maybe pull up an equation that you could refer to. I think, well, how would this match this, or how would this equation tell the story of like how this problem might work out? I mean, there's only like 3 kinematic equations, right? You guys see them there on that green poster over there. Right? Let me okay. So if you get everything right, then that's awesome. If you miss a bunch of questions, then what I'm giving you guys points in the gradebook for is just for completing it. Right? So there's no real incentive to cut corners or cheat. If you do something like that, if you're just like, oh, I'm just going to look up the answers and just bubble these just to get this assignment out of the way, really all you're doing is just cheating yourself. I've seen this in the past. Students that think deeply about the questions that I assign, everything that I assign to you guys, I'm giving you guys an opportunity to think deeply about how something would work. Like it's a learning opportunity, right? It's an opportunity for your mind and your brain to expand. Okay, how does this work? I got to figure this out. Got to solve this puzzle. So yeah, don't cut corners in this class, even if sometimes it might be easy, like, oh, hey, progress record, and just look at the answers because that's not gonna help you out. Yeah, so yeah, that'll be up there. Got a due date is September 5th, which is a Monday morning. So I have it done by then. And what my plan is to do, and this worked out pretty well last year, is if you guys have it finished by then what I can do is I can pull up that AP classroom assignment, and then we can go over it as a class together. And I could see like which were the most missed questions and go over it after the fact. Okay. All right. So yesterday, yeah, we did this. I'm gonna switch back over here. Let me do a quick recap of some stuff you guys saw yesterday. Then I'll show you guys some Paul Hewitt videos that I've referred to a couple times, but I haven't showed you guys yet. And then we'll continue from there. All right, so yesterday you guys we had a nice long 3 period block class. You guys were rolling these toy cars down these inclines. And you were saying, well, what's the relationship? All these different variables. What's the relationship among these variables? Like if you change out the mass of the car, or if you change this rolling distance, or maybe the amount of time it's been rolling for, or hey, I wonder what the speed is going through the speed gate here at this motion detector. Okay. Now everybody did leave the angle constant. It was about a 5-degree angle. Okay. Now you guys know in a really well-designed experiment, if you can, ideally you control all the variables except for 2, right? 1 independent variable and 1 dependent variable, and that's what I had you guys do. I had you guys do well, one of these 4 experiments. Okay. So just to recap what you guys saw there, you guys found no relationship between mass and time. Like you could have 10 times the mass of the car. You can like take a big old lab weight on it, and it made no difference in its motion. Which actually, what you would show there is exactly what Galileo found back in 1589. He dropped different objects off Leaning Tower of Pisa, light stuff, heavy stuff, and it all fell at the same rate. Okay, now, why that is more a question for like unit 2, but for kinematic motion, you just care the fact that everything, like gravity pulls everything at the same rate, causes everything to speed up at the same rate, has the same free fall gravity, same acceleration. Okay. Now, of course, on the incline, everything slowed down, but it was under a gravitational pull, so it was like speeding up. Everything was speeding up at the same rate, regardless of the mass. Let me go hit this one right here, V versus T, because that gave you guys one of the most important graphs that you're going to get in this class. I know I have it lined up right here. Here it is. Here's your V versus T. Okay. So do you guys see how it's like this linear relationship, right? And V versus T, that's velocity versus time. So at time 0, see how it starts off at 0 velocity? That's what that origin point is. So release from rest, right? And sometimes you see the phrase release from rest. And what that means is that initial velocity is 0 meters per second. Okay. So like if your eyes are darting around looking for numbers, like I need numbers to plug into equations, like I think I'm missing some kind of information. Look for a phrase like release from rest, because that, or later on you might see like it comes to a complete stop and say, oh, that means final velocity is 0 meters per second, something like that. Right? But see how this has a constant slope. Okay. Well, think about the units for what's, because if you forget this, or let's say you get like some graph that's like some variable versus some variable, and I wonder how do I interpret like this graph that maybe I've never seen before, or seen like once before in my life. Well, think about how units work, because isn't slope rise over run? Right? Look at this rise over this run. Is that like meters per second per passing second, rise over run? Hey, that's like meters per second squared, which describes an acceleration, which is exactly what this is. So the rate that velocity will pick up is called acceleration. That's the definition of acceleration right there. And the fact that there is constant acceleration, well, that's something that you'll always see in this class. We never really deal with variable acceleration. There might be a weird question here or there where the acceleration changes, but in this class, you're really dealing with just constant accelerations, right? If there is acceleration at all. Okay, so you guys got that graph. Come back and talk about that a little bit more, but that's basically so this one. Right? So if the car was rolling for more time, then what's speed pick up to? You know what actually I'm gonna do is talk about the weird one. Right, so this bottom right one. So what was the speed as a function of not time, but as a function of like how far the car had been rolling? Now V versus X, you almost never see it. Like you might never see that graph ever again, or maybe you might see it like once. Okay? But it came into like a square root relationship. Okay? And you look, that's actually consistent with is it being consistent with this last equation here? No, let me show you guys what that would be. So car was released from rest. So see if you guys are following. What was the initial velocity for release from rest? 0. So bump that out of the way. Okay. Do you guys see now? If you square root both sides, that the speed that it picked up to as a function of distance would be a square root relationship. B is equal to the square root of 2ax. They said. Okay. All right. Now that equation actually you see quite a bit. Anything that involves like go to the edge of a cliff, drop a ball, how fast is it crash landing into the valley below, right? As the function of the height of the cliff, right? But notice what variable I did not mention in any of that scenario. I did not say how many seconds that ball would move on for, right? Because this equation doesn't explicitly mention time, even though time is taken in the background, right? But if you know something's been falling for some distance, how fast it picked up to, right? So it's a square root relationship. And then the other one you guys did, this one here, displacement versus time. So you let the car go for some time, said how far did it go? What did that graph look like?
Parabolic.
Yeah, that was a parabola. Okay, so that looked like some kind of parabola, right? At some point, we did the set of graphs. Now, I gave you guys a scenario: you drop the ball from edge of cliff, but really that's the same thing as releasing the race car on an incline, except the race car on an incline is just like slowed down, right? The acceleration is slowed down. Okay, but if you do like pure free fall, then the acceleration is just the full rate of gravity, like 9.8 or 10 meters per second squared. Right? Okay. So these two graphs right here, I think it's the last thing I left you guys off with yesterday. Okay? So displacement versus time, yeah, this would be a parabola, and its slope increases at a constant rate, right? So that velocity versus time increases at a constant rate, right? And that slope is equal to, well, usually I round it to 10 meters per second squared if you're talking about free fall gravity on Earth. Okay, so the slopes of x versus t. Let's see, meters per second. That tells you meters per second. That tells you the coordinates of velocity versus time. And the slope of velocity versus time, let's see, that's meters per second per passing second. That's meters per second squared. Oh, hey, that's acceleration. That's the coordinates of acceleration. You guys see constant slope, constant coordinate, right? That's it. And then you can go the other way too, right? So if you're looking at the area under acceleration versus time, see that's meters per second squared is the height of the rectangle. Seconds is the base of the rectangle. See, base times height. Meters per second squared times seconds. Doesn't that give you meters per second? Oh, that describes the velocity. Really, it's a change in velocity because what if you didn't start from rest or something? But if you did start from rest, it's just a triangle shape. Okay, and then the area under this one. What's meters per second times seconds? Meters. Hey, that describes the displacement. So the area under this curve, as you accumulate it, tells you the change in coordinate of your displacement versus time. Like how far is it falling down the cliff? Okay, you guys feel that? Maybe flip through some other notes you guys saw yesterday. Oh yeah, so this set of graphs pairs with this table, which links back to those 3 kinematic equations. Okay, so we're watching time tick, 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 tick. There's time going in seconds. Okay. The acceleration was constant. Oh, look at that. So acceleration is the same all the way down. This is free fall on Earth in meters per second squared. It's really 9.8, but most of the time, more often than not, I'll round it to 10. AT does the same thing. Okay. So the velocity picks up 10 meters per second per passing second. Okay. I mean, that's what acceleration is, right? So 10, 20, 30, 40, 50 meters per second. Okay, goes the velocity. If you point a radar gun at that ball as it's falling down the cliff, right? And then the last question is, well, how far has that ball fallen? Right? How far did your race car roll? That kind of go, right? But we're looking at a ball falling off a cliff. Okay. Now this one, probably the best way to get these numbers is to just plug it into like this equation. Okay. So remember these equations describe those graphs. Okay. Especially anything to do with like as a function of time. All those graphs had time on the horizontal axis, right? So these top two have time, right? Okay. So release from rest means initial velocity is what again? 0. So if I bump this guy, it just boils down to 1/2 AT squared. You guys see 1/2 AT squared? Right. So here, let's take 3 seconds, for example. If you plug that in, 3 seconds. So if I plug in 3 seconds here, guys, what's 3 squared? 9 times 10 meters per second squared is 90 meters divided by 2 is 45. If it's released from rest, this goes to 0. So x would be 45 meters. So 3 seconds. Oh, 45 meters. Hey, look at that. Okay. Guess that. Okay. let's get one more look at these equations. Then I'll flip over and we'll watch a little bit of Polkut. Watch a few minutes of Polkut. Okay. So let's go over these again. I'm going to start with this middle one, then go to this top one, and then this bottom one. All right, so the middle one. If there is no acceleration, then what does that part say? Just the part that you can see right there. Final velocity is equal to initial velocity. Okay. Okay. So which would be 0 if you start from rest. If you start from rest and there's no acceleration, then you're always at rest. What if the car's already in motion, like 30 miles an hour? Then if the car's not speeding up or slowing down, then are you still going 30 miles an hour? Even after like 10 seconds, 20 seconds, 30 seconds? Yeah, because that's constant velocity. Okay, so the velocities match as long as you're not accelerating, as long as you're not changing velocity. Okay. How about this? What if you start from rest and you are accelerating? Well, that looks like, here, let's do a free fall example. If you're picking up 10 meters per second per passing second, well, 10 meters per second squared, and you do that for some number of seconds, well, doesn't that just lead exactly back to this column? 10, 20, 30, 40, 50, right? Okay, so that says that, right? Now, what if you have both one of them? So you have an initial velocity and you're accelerating. Well, then you just add the two together, right? And that, actually, we did a graph of that yesterday. That's this one right here. You guys remember this graph yesterday? Right? That's like, hey, it's not like y equals mx plus b. That's exactly what this is, right? Mx plus b, except instead of x, it's t for time, right? You guys know that? Okay. Right, so this is like if you throw a ball straight down from the top of a cliff. I'm going to do that graph with you too. After we do Paul Hewitt, we'll go back to that cliff and say, instead of dropping the ball off the edge of the cliff, what if you throw it down, or what if you throw it upwards? Right? Might give you a graph look something like this, right? Are you guys okay with this equation, this middle one? Okay. Because I'm going to use that to go back to the top one. Okay. So remember, the area under v versus t tells you something about displacement. And I see two shapes. Well, you say a trapezoid, but I can split that into this bottom rectangle and this top triangle. Okay. So the bottom rectangle, well, that's easier. That's just distance equals speed times time, right? This v times this t. Okay. In fact, if you're going constant velocity, that's all it is, right? Isn't it just distance equals speed times time? Okay. If you're going constant velocity. Okay. But what if you start from rest and you accelerate? Well, that's the area of this triangle. That's the 1/2 at squared bit. Okay. And then what if you like throw a ball at the edge of a cliff? Well, you can just put the two together. You just tag them together, right? That rectangle plus that triangle. That rectangle plus that triangle. Okay. You guys get that? Right. Okay. So hopefully this middle one is super intuitive. You can see that. Right. Hopefully the top one you say, okay, I can kind of get that. Right. Rectangle plus triangle. Okay. Now this third one, I think, or at least my understanding is, it's good to see this as a system of equations between the top two. Do you guys remember system of equations from algebra? You guys remember like substitution, elimination sort of deal? Here, I can tell you how you can solve this third one. Right? You guys got it yesterday, sort of through your race car. You're saying, hey, different distances. What's the final speed? You guys sort of got this. There was that square root relationship. Okay? But if you take this middle one, you solve for time. Let's see what would time be. Would it be VF minus V naught all divided by A? Do a little bit of algebra and solve for T. And if you were to take that and substitute into this T up here and do like a bunch of algebras, you could eventually rearrange it and it would look like this third one. Okay. See how the time is substituted out? Okay. Any questions so far? All right, so that's a recap. New stuff you guys saw yesterday. I do recommend that you memorize those equations, although on the AP exam, you'll have the AP equations available to you. All right, so let's switch over and do a little bit of Paul Hewitt here.
If that's what acceleration is, we can tell how fast things go by just saying this: the velocity that something the velocity acquired when falling is simply equal to the acceleration times the time. And if the acceleration for free fall is always 10, then the speed something picks up is simply going to be 10 multiplied by that time t. That's what we just did. I asked you people like this, if you go for 10 seconds, fall for 10 seconds, how fast is it going?
And what's the answer to that question? 100 meters per second, right? Edge of the cliff, drop a ball.
Where the t is, you put 10. And that cancels out one of these seconds over
Ooh, see what you just did with the units? Remember, all numbers in this class have a unit attached to them. There's a couple of weird exceptions, but yeah, so don't just follow the numbers in this class, which are on your calculator screen, but also think what's going on with the units. See how one of the seconds cancels? It gives you meters per second, which describes the velocity. Right?
Here, and so what you're left with is 10 tenths is 100 meters per second. So a freely falling object will pick up to a speed of 100 meters per second if it's got 10 seconds to fall.
So actually, I want to go back here a bit. Let me look at one of the other equations that's on the board. You guys see over here, he has v bar equals distance over time. You guys see that? Okay. Now, different characters used for distance. A lot of times they use x for displacement. He's using d for distance, some distance. Okay, so you guys get that, right? Now, who knows what the bar stands for? What's the bar about? Oh yeah, go ahead. It means average in this case. It means average. Okay, so it's be like an average speed, average velocity. Say you go on a big old road trip, right? You go like 1,000 miles and it takes you like some number of hours, right? Well, sometimes you're going constant velocity, sometimes you stop and get gas, sometimes you're sleeping in a hotel overnight, right? And you could take the full distance of your trip and say divide by how many hours, so you could get like an average, right? So maybe you're traveling on the interstate like 70 miles an hour most of the time, but when you average everything out, maybe it comes out to like 40 miles an hour once you consider like like all the breaks you took and something like that. And you could rearrange this. You guys see right below them, it's covering up a little bit, but total distance is average speed times time, right? So the reason I'm pointing this out is that we almost never deal with average velocity. You might see that here and there, but all those those three equations, they're talking about instantaneous values. So v naught and vf, right, with those subscripts, that's talking about at the beginning and the end of an interval, initial velocity, final velocity, right? And you almost never see average in this class, maybe here and there. So just be aware of that. Okay? All right, next one.
The average speed when acceleration is constant is simply the speed you begin with plus the speed you end up with divided by 2, the average amount, and then multiplied by the time of fall.
Okay. So there's what I was just pointing at, right? So average speed times time. Okay. And he's saying here, if something is, for example, in free fall, right, edge of cliff, right? Well, if you look at the beginning speed and the ending speed, right, and average those out, that would happen to represent the average time. Okay. Now, if you believe that, okay, yeah, I can see that. Then what he's about to do, just so you know what to look for, is he's going to derive displacement, like how far it's fallen, equals 1/2 AT squared, differently than I did. I showed you guys the graphical method yesterday. So what's the area under this triangle on this graph? You guys remember that? Under v versus t. He's going to do it a little bit differently, but he's going to get the same answer. Okay.
But we're always going to take the case where the initial speed is 0.
Well, not always, but just for this example, right? So leaves from rest.
So we're simply going to end up with the speed we end up with at the end of any time interval divided by 2 multiplied by the time. And what's the speed that an object will have after it's fallen? Just in general. For 1 second, we know it's 10. But how about t seconds? Anyone know? Do we have any relationship for how fast something falls? Right here. In fact, if the acceleration is g, the speed is going to be gt, the one we had right over here. So let's put that over here. See what we have here? Is this time and this time the same? This is the time that it was falling. And this is the time it was falling too. They're the same time. So I can make this a little bit more shorten up. And now I have a relationship for how far something falls.
Look at that. Same thing.
You're on the mainland. You're up country, mine country, California. You're out with your friends. And you have friends there, and someone opens up an old mine shaft. musty. Someone says, geez, I wonder how deep that is down there. Dark, dank. You hear the bats. Straight down. Someone says, gee, I don't know, if we had a rope, we could lower the rope and find out when it hits the bottom. So look, the ladder is all broken. There's no way to find out how far down that goes. You say, wait a minute, hand me that rock. Friend, hand you the rock. You take the rock. 5 seconds it takes to hit the ground. Disregarding the time it takes for the sound to come back up. Took 5 seconds to hit the ground, right? Someone says, well, how deep is it? And you say,
So what's the answer to that question?
Maybe 25 feet or 50.
Wait, how many? 125 what? Not feet, meters, right? Because we're using metric, right?
5 seconds. 5 5's 25. 25 times 5. It's about 125 meters deep. Some say, how'd you know that? And you say, college.
College, that's right. It's physics. Any questions about that? If someone's been falling 4 or 5 seconds, it will have fallen 125 meters. Actually, we did do that yesterday. We did that right here. There, falling for 5 seconds. Displacement 125 meters. Yeah, guys remember that? Yeah, yesterday. All right. Let's do some more cliffs. So yesterday, the last one we did was, well, you just drop a ball from the edge of a cliff. We got okay. We got this table of values for dropping a ball, and then these corresponding graphs. Okay. Now let's get to where we're like, throwing balls around. Side. You know what? Let me try this just at all that's on the screen. Just split this paper. I'll do it like table and graphs. So table, graphs, and this is going to be for let's do scenario. You're going to throw a ball upward from edge of cliff. And let's have down be defined as the positive direction, just like yesterday. Okay. Now, AP questions, you might see either way. Sometimes down is defined as positive, sometimes up is defined as positive. I may have the cliff edge as 0.0. Sometimes AP questions, you'll see the cliff edge as 0.0. Sometimes they define the valley floor as like 0.0 for displacement. Okay. But just to start us off, it's something pretty fundamental. You guys remember yesterday, this table had 4 columns, so dancing 4 columns today. Time, acceleration, velocity, and displacement. So time is going to be tick in seconds. It's going to be some acceleration, meters per second squared. Some velocity is picked up to meters per second, and some displacement from the cliff edge in meters. Then we're going to have graphs. Let's do the same 3 graphs as yesterday. Now, make these don't make these strictly first quadrant graphs. It's going to be quadrant 1, and it's going to dip a little bit into quadrant 4. Or at least that's true for x versus t and v versus t. So, playing ahead a little bit here, okay. Because here's kind of how you might see that's going to be the case. Because if you throw the ball upward, is it eventually going to come back down? Right. What I should do is. But this is like the edge of the cliff right here. So here you are, edge of a cliff. You're gonna throw this ball, and it's gonna go and come down. That right. And we're gonna do displacement in meters versus time in seconds, velocity in meters per second versus time in seconds, and acceleration in meters per second squared versus time and seconds. All right, so there's our setup. what I should do is switch the color, maybe might help it stand out. Okay. Let's go. Time to be 0, 1, 2, 3, 4, 5 seconds. Ticking along. Let me throw in one more detail before we get going too far. We need to know like how fast are you throwing this ball. So let's go. Here, throw a ball upward. Let me add a detail here. Let's say at 10 meters per second. 10 meters per second, straight up. Okay. Which means that this number right here has to be, well, the magnitude has to be 10, but one more detail. Guys, if down is defined as positive and you threw the ball upwards, then what's the velocity of the ball leaving your hand? Negative 10 meters per second. There you go. Great. Guys get that? All right, so there's our setup. All right, threw the ball upwards at 10 meters per second. We're defining down as positive. That's why throwing it in the negative direction. Okay. Okay. And then we're going to count off 5 seconds. We're going to see how's this ball accelerating, how fast is it going, and how far has it, what's its displacement from the cliff edge. Okay. All right, now, as soon as the ball leaves your hand, is it under free fall? Yes. So for anything that's in free fall, all that means is that there's only one force acting on it, which is its own weight, which means that it's accelerating. Which way, how much? Is it accelerating down at 10 meters per second squared?
Yeah.
Yeah. Hang on. Can something be doing that? Can something be moving physically upwards, have an upward velocity and a downward acceleration at the same time? Yeah. If that's the case, if something's moving one way but being pulled the other way, what is it doing? Speeding up or slowing down? Slowing down. This is the first slowing down example we've done so far, right? Because you guys, race cars yesterday, those were only ever speeding up. It started from us to just speed up. Yesterday, dropped the ball off a cliff, started from us with speeding up. This one, ooh, slowing down. Okay. I'll make a table for you guys probably after this example too to look at that like directions of these. Okay. In fact, if the ball is in free fall, is it just going to accelerate at 10 meters per second squared towards the ground always? Yeah. That's just, hey, that's like yesterday. That was also the case, wasn't it? Just 10 meters per second squared towards the ground always, as long as it's in free fall. Okay. We're also ignoring air drag, of course. How about velocity? So you guys are following. What number do you think goes right here? 0? You guys saying 0? Okay. All right. Now, if you're not sure why that's 0, then which of these 3 equations would you refer to figure out that it has to be 0? First, second, and third. Second one. So I might call this like first, second, and third equation. The second one, because this number was, what was this number? Negative 10 meters per second. And this number was 10 meters per second squared times 1 second. Do you guys see negative 10 plus 10 times 1 brings you to 0? Okay. What does that mean about the displacement of the ball? It means it's reached what special point? The peak. Yeah, the maximum height. Because now isn't this ball going to turn around and start going towards the ground again? So that right there, 0 velocity tells you that the ball has reached like as far as it's going to go. Okay, in calculus, the term for that is called the critical value. I'll show you guys on the graphs how that pairs up. Okay. What about after 2 seconds? What do you think number goes here? It's saying 10. Okay. If you're not sure why it's 10, let's try this. What's negative 10 plus 10 times 2? Negative 10 plus 20. That is positive 10. It's 10 meters per second towards the ground. How about after another second? 20, another second. 30, another second. 40. This looks like the pattern of yesterday, right? I mean, once you start from rest, in free fall, it's just going to pick up 10 meters per second towards the ground every passing second. Okay. Guys, okay with that? All right, how about displacement from the cliff edge? Well, at time 0, if the ball is just leaving your hand, right? So let's say the ball is just left your hand, it's like a millimeter above your hands, right? See, it is moving this fast. It is in free fall, so this acceleration applies. But isn't it at the cliff edge leaving your hand? What number do you think goes here? It is 0. So 0 meters from the cliff edge would just be 0, right? Okay. Now, if you define 0.0 as like the valley floor, you might put the height of the cliff here, but I'm doing from the cliff edge, right? So it starts off at 0.0. Okay. Ooh, what number do you think goes right here?
-5?
Ooh, so you're saying -5 meters? Anybody think anything different? -5 meters. Okay, let's try this out. Which equation did you use to figure that out?
First one?
Yep, first one, because we know how much time has passed, 1 second. Okay, let's put it all together. So -10 times 1, that would be -10 meters per second. I mean, if you were in gravity-free zone, like in deep space, that would be the answer. Be going -10 times 1, boom, done. Okay, -10 meters. But remember, Earth is pulling the ball towards the Earth, right? So we're gonna go +1/2 times 10 meters per second squared times 1 second being squared. So this would be 5 meters, right? So what's -10 meters plus 5 meters? Ah, that's -5 meters. Okay. Hey, what's the maximum height of the ball from the cliff edge?
5 meters.
That's 5 meters up. You guys see that? It's 5 meters into negative territory. This from here to here is 5 meters. You guys get that? Yeah, because down is positive. Right. Yeah. Unless, of course, you change the definition of what's positive and what's negative, but yeah, in this case, negative is up. Positive is down. How about after 2 seconds? What number goes here?
15?
I'm also thinking 20. Let's try this out. So we're going to plug in 2 seconds, right? Here, I'll write this one out. Put another paper here. Okay, so you guys know we're still using this this top equation, or well, it's top formula. We're going to make an equation. X equals -10 meters per second just for 2 seconds, plus 1/2 times -10, or sorry, positive 10 meters per second squared. This sounds positive. Sorry, this should have been morning. This is the first period class, so let's go this. Okay, that's negative. That's positive. Okay. We're doing this for 2 seconds, and don't forget to square this 2 seconds. Oh, guys, the square, does that only apply to the t?
Yes.
Yes, it does, right? Order of operations. It doesn't apply to anything else, right? The square is only on t. Right? So what do we got here? We got -20 meters. Okay, so meters, right? Because seconds plus, say 2 squared is 4 times 5. Did I mess up? No, well, sorry, 2 squared is 4. 4 times 10 is 40, right?
It would be 0 overall.
Yeah, okay, I'm being silly. I messed up. I messed up somewhere, didn't I? I sure did. Okay, yeah, you guys are right. All right, that is 0. That is 0. 0 meters. Okay, I should have known that too. This has to be 0. Oops. Because you can see just based on symmetry, right? Like if it took 1 second to reach the peak, isn't it take another second to go back to the cliff edge? Oh, yeah, the graph will be a parabola, right? And yeah, the parabola's gonna go like this. It's gonna take 1 second to reach the peak and 1 second to come back to the cliff edge. Yeah, so that number is 0. Okay. Right, how about let's throw in another second. Let's go to 3 seconds. X equals -10 meters per second, 3 seconds, plus 1/2 10 meters per second squared, 3 seconds being squared. So that's -30 meters plus, see, 3 squared is 9 times 5 is 45. Yeah, this looks right. So that'd be 15 meters like below the cliff edge, right? Okay, all right. So this is 15 meters. So that's from this cliff edge. We could go 15 meters down. Okay, that's the next second. Now, if you plug in 4 seconds and then 5 seconds, I know how this table is going to finish because the answer is actually posted on my wall on that poster, which is also in a file for you guys in Google Classroom. You guys see this one right here? Do a ball upwards. I went with this number right here. Boink. No, oh, look at that. Okay. So it's going to finish out like this. Okay. And you guys can check me if you want. It's going to be this far and this far in meters. Okay. Is that right?
Yep.
All right, so let's go put these graphs together. I'll do the same thing I did yesterday. I'm going to start with the middle one. Then I'll do acceleration versus time. Then we'll do displacement versus time last, because that's the trickiest one to think about. Okay. So velocity versus time. So at time 0, or see if you guys could say a step ahead of me. See if you guys can draw this graph before I draw it. If you guys are drawing pencil, might be a good idea in case you need to erase something. Okay. So at time 0, I do see that there was the negative 10 meters per second. So here's your V naught, which is negative 10, let's say, meters per second. Okay. And then what do you think the rest of that graph would look like? There's a point here. Yeah, it's still a linear relationship. Okay. Okay, so we got the point at 1 second, there was 0 meters per second. At the point 2, there is positive 10, 0.3, 20. See, after the 4 second, we're up to 40 meters per second. Look like that, wouldn't it? Right. Hey, what's the slope of this line everywhere? 10 meters per second per passing second. Rise over run. That's about 10 meters per second squared. Okay. Which tells you the coordinate of acceleration versus time. Which is also in the table anyway, right? No matter how much time has passed, as long as it's in free fall, it's always picking up velocity towards the earth at a rate of 10 meters per second per passing second. That's about 10 meters per second squared. The number is 10, the unit's meters per second squared. All right. The slope to this guy is equal to the coordinates of this guy, just like yesterday. Okay. Yeah. This x comes from this top equation. Okay. Now, yesterday we just did 1/2 AT squared. Whether you were releasing those race cars from rest or if you were just dropping a ball from the edge of a cliff, because V naught was 0 meters per second for release from rest. But today I'm having V naught be negative 10 meters per second. So because you're throwing upwards at 10 meters per second. Okay. So upwards negative direction. So here, I've got a couple examples right now. Let's look at the third second. So it's been moved for 3 seconds, right? So if you plug in here, okay, this matches up. If you throw upwards at 10 meters per second, that's negative 10 meters per second for 3 seconds. Okay, so that's 3. Okay. And then plus 1/2 AT squared. So acceleration is positive 10 meters per second squared. This is towards the ground, 10 meters per second squared. And then 3 seconds again, so 3 seconds, so the same time. Okay. From the time that you release it, you count off 3 seconds. So you're going to square that 3 seconds. This bit comes out to 45 meters towards the ground. The direction you threw it is 30 meters towards the sky. So it's negative 30 meters plus 45 meters comes out to 15 meters. Okay. That's how, for example, at the third second, we got 15 meters below the cliff edge. Okay. That's that one. And then you could take all these other times, say like if you plug in 2 seconds, that's what the top one was. Plug in 2 seconds, comes out to 0 meters. Plug in 3 seconds, it comes out to 15 meters. Right? The initial velocity is the same, the acceleration is the same, but the time, say from 2 to 3 seconds, went from this to this. Okay. You know what else I wanted to point out on this page of notes? Okay. Notice how so many meters plus so many meters. You guys see that? Meters plus meters. Okay. Now, can you multiply together values that have different units? Definitely. Because look, we got meters per second times seconds, meters per second squared times second squared. Okay, so you can multiply things that have different units together. Okay. The whole dimensional analysis thing, we did examples of that. But can you add together values that have different units? You cannot. Okay. For example, what is 4 miles plus 3 gallons? 4 miles plus 3 gallons. That's 7 what? That's not, that's 7 of nothing. That's not anything. That ain't even making sense, right? So when you guys are adding values together or subtracting, adding and subtracting, make sure they have the same unit, right? Is that okay? Any questions so far? Questions so far? All right, you guys ready to put together X versus T for throwing the ball upward? Hey, do you guys think that the graph of this is going to look pretty similar to my dash line right here? I mean, the dash line I did pretty much up and down. I mean, I gave it a little, tiny bit of lateral motion just so it stands out. But this looks like a really skinny parabola, doesn't it? Ooh, we're about to draw the parabola. You guys get that, right? So at time 0, I'm going to define the top of the cliff as location 0. Just has a point there. Now, you might get some AP questions where they don't define the top of the cliff as point 0, but I'm going to do it just a pretty fundamental example here. Okay. Then remember, we're throwing into negative territory. So the first thing that kind of happens, ball goes towards the negative direction. In fact, after 1 second, it's gone 5 meters in the negative direction. Let's say upward, right? Okay. So at 1 second, wouldn't this be at -5 meters? Like right there. Right. After 1 second, -5 meters. That's true. Okay. And after the next second, well, now the ball is just falling back to where it started. So we're back to 0 again. After the 3rd second, we're up to +15, 5, 10, 15. Ooh, now this is really taking off. So it's like right here, 15. Ah, you can definitely see a parabola shape, right? Take off that. Right. Which is really just this physical scenario just turned upside down, right? And then the horizontal axis is just a time axis because you're counting how much time. Okay, is it? Now, the relationship among these graphs, that's another thing I want you guys to see is like, what's the relationship among these graphs? Okay, you guys know to go from the top graph to the graph below it, you're looking at rates of change. And you guys were saying yesterday that calculus relationship is called what again? Derivative, right? Okay, so when you guys take a derivative of calculus, you're finding rates of change, going like displacement, velocity, and velocity to acceleration. Okay? Now, what is the rate change of motion of the ball at the very top? It's not going up anymore, and it's also not going down. It's like turning around, right? So if it's not going up and not going down, then what's the rate change of its motion equal to?
0.
0, right? So we're still saying here. Okay, so it looks like it's going up slower, slower, slower. At the very top, it's 0 rate change of location, and then after that, it starts to pick up, going down. Okay, now rate change of location. What's the physics term for that?
Velocity.
Velocity. So at the very top, you can say it's velocity is 0 meters per second. Okay, like if you point a radar gun at it right at the top, right? Wouldn't it be 0 meters per second? Okay, and look at this. Let's go back to these graphs. You guys see where its peak location is and where its 0 velocity is? If I line those up, see how they exactly match with each other? Right, this 0 rate change, like if I hold this ruler flush to like this maximum location point, it has 0 slope, and the coordinate of v versus t is also 0. You see that? Okay. That's something else you'll eventually see in a calculus class, right? Where, in fact, that's one thing that you do with, that's one of the purposes that you can apply with calculus. You can find optimal values. Optimal values might be maximum, they might be minimum. Suppose you're trying to like minimize the cost curve in economics, right? You might say, oh, I really want to get, what's the bottom of this? Hey, if I take the derivative, the rate change, and set that equal to 0, that would exactly tell me where that point is. Okay, you guys get that? Okay. Okay. And then the last relationship I want to hammer down. This one takes some extra thinking. Okay. Remember I told you guys if you go the other way, if you go from the bottom graphs up to the graphs above, what's that calculus process called? Integration, right? And it has to do with like finding areas. Remember, like find the area of this rectangle. It tells you something about like the change of velocity. Okay. But very importantly, it's change. Remember, this graph looks exactly this A versus T. Doesn't that look exactly like the A versus T yesterday? Here, see it side by side. Here's dropping the ball. Here's throwing the ball. Do these graphs look identical? They sure do. In fact, if you just focus on the acceleration graph, could you ever know whether you threw the ball or not? So this acceleration versus time graph, you don't have any velocity information. but the area under the curve tells you the change in velocity. So do you guys see that both of these velocity curves, they start out different places, but their change of velocity is the same for any interval of time. They have the same slope, right? Okay. In fact, when you do integration in calculus, they'll tell you to do like a plus c at the end, right? And the plus c is because, well, here's a physical interpretation. You don't know what the intercept of this graph is just based on acceleration. Okay. Right. And then it's the same story going from velocity to displacement, but it's a little trickier to think of. It looks like kind of like a shifted parabola. Remember yesterday the vertex was right at the origin, and today the vertex is kind of over here. Okay. Let's go to that. Oh, here's what I'm gonna say too. When you go from left to right, see how you start off with like negative area? That is negative area. Isn't that a negative triangle? That corresponds to negative displacement. Okay. Here, let's see what is the area of this triangle. Remember, it's 1 second wide. It's 5 meters per second, or sorry, 10 meters per second tall, and it's negative, right? Area of a triangle is that 1/2 base height. What is 1/2 times negative 10 times 1?
-5.
-5. And then the unit would come up to meters, right? Because meters per second times seconds is meter. Hey, -5 meters. Look at that. Look at that. Right? The area of that triangle corresponds to the maximum height. Okay, see that? Right? And then after that, just trim them. Ooh, how about trim this? You guys see that negative triangle plus this positive triangle up to that point will cancel each other out. Right? Look at that. We're back to zero displacement, back to the top of the cliff. Right there. Okay. Questions so far? All right, so I want to do another clip with you guys. But before I do that, I want to give you guys a table of velocity versus acceleration, so we can think about some different scenarios. Okay. Then we'll do a clip and one other example, and then I got some other stuff on it for you guys. Nice long day, lots of stuff right here. You like this table. Let's call this velocity. And call this acceleration. And we'll go positive and negative, and here we'll go positive and negative. Okay. So like you might have a positive velocity or a negative velocity. That could just mean like you're physically moving forward, you're physically moving backward, right? Or up or down. If up is positive, down is negative. And then acceleration, well, you guys know at least one example of acceleration could be like free fall gravity, right? So the gravity's pulling you a certain way, you like tend towards that way. If you let the clock run far enough, long enough, you'll eventually might actually move that way. Okay, so acceleration is like which way you're being pulled, sort of. Okay. Now, what if you have positive velocity and positive acceleration? What could an example of that be? Yeah.
Pushing the gas pedal on.
Pushing the gas pedal on a car. So you're moving forward and you're also speeding up forward, right? Hey, wouldn't this be like speeding up or like as you just like speeding faster, speeding, you're going faster and faster, okay? Speeding up, moving forward. Okay. Another example could be drop ball at the edge of a cliff, right? It could be physically moving down. This is called down positive. And also it's accelerating in that same direction. So it's like speeding up, it's going faster, faster, faster. That'd be true. What if you have, well, let's stick with positive velocity. Let's go with negative acceleration. So these two have opposite signs. You're moving one way, but you're tending towards the other way. What do you think goes in this quadrant? Yeah, so you're still moving forward. The direction of your velocity tells you which way you're moving, but you would also be slowing. So if he's slowing down, still moving forward. Okay. What could an example of this be?
Applying the brakes.
Applying the brakes. Yeah. So you're physically moving forward in your car. That's what the direction of velocity tells you. But you're slamming on the brakes at the same time. That's like slowing down while you're moving forward. Right. How about this quadrant top right? If you have negative velocity, does that mean you're in reverse moving backward? Yeah. If you have positive acceleration, what do you think?
Your car's in reverse.
Exactly. Yeah. Or sorry, no, scratch that. I'm sorry. Okay, hold on. Your car's in reverse, and you're also doing what at the same time? Hitting the brake. Right. Hitting the brake. Yeah, so you're hitting the brake while you're in reverse. Yeah, so you're in reverse. Yeah, so it'd be acceleration, but it would be like causing you to slow down. So moving backward. Okay. Your direction of velocity tells you which direction you're actually moving. In this case, backward gets negative. Okay. But the fact that these signs are opposite of each other means slowing down. Okay. And then finally, this last quadrant, if you are in reverse and you are also accelerating that same direction, wouldn't this one be speeding up in reverse? So now you're hitting the gas pedal in reverse. This is speeding, like speeding up, but in reverse, so backward. Okay, so big picture then is the direction of velocity tells you which way you're moving. So forward, forward, and then this right column is backward, backward. Okay. And then whether you're speeding up or slowing down really has to do with, are the signs for your velocity and acceleration the same or opposite? If they're the same, then you're speeding up. Positive, positive, speeding up. Negative, negative, speeding up. Okay. If you have opposite signs, so if you're like moving forward but accelerating backward, that's a slowing down situation, or vice versa. Okay. Okay, you guys got that? Oh, you know what question I should have asked by this point in the class? Actually, you know, because let's say it for let's do a cliff example, and then I have a car example for you guys. Okay, so we'll do one more cliff, and then we're going to do a car. So this cliff example, let's say you throw a ball down from the edge of a cliff. And let's define down as the positive direction, just like we did for the last couple of examples. So this is our own definition. Down is positive, positive direction. Okay. I'll do the same thing I did the last one. I'm going to split the paper, give you guys a table and a graph, or a set of graphs side by side. Okay. So it's a very similar looking table. How much time has passed in seconds? What's the acceleration in meters per second squared? You guys are labeling all your units also, right? With those. What's the velocity in meters per second? And what's the displacement in meters? Count off the same amount of time. So 0, 1, 2, 3, 4, 5, just like last couple examples. Okay. I forgot to say throw down at what speed. You guys tell me, what do you guys feel like for the throwing speed? Let's go 20 meters per second. Let's say 20 meters per second. So why not? So we gotta throw the ball down 20 meters per second. Okay, so there you go. That's our starting value. Get a set of graphs. So it's gonna be the same 3 sets of axes that we've been working with. These can all be first quadrant graphs. They're all gonna work out that way. Okay. So we got displacement in meters versus time in seconds. We got velocity in meters per second versus time in seconds. We got acceleration meters per second squared versus time in seconds. See if you can predict what those graphs are going to look like before we start plopping a bunch of points down. Gonna look like, right? Okay. So let's go fill in this table. What number goes right here? 10 meters per second squared, because we're on Earth. We're rounding a little bit. Ignore air drag. There you go. 10 meters per second squared. Good call. How about after 1 second? 10 meters per second squared. It's gonna be that all the way down this column. Yeah. So remember, as long as you ignore air drag and you're on Earth, round a little bit. There you go. 10 meters per second squared. Straight shot. Okay.
Why is the acceleration the same as throwing it down?
Okay, because throwing it down, no, I'm only considering once the ball's left your hand. Now, while it's in your hand, yeah, maybe it's accelerating all bonkers because you're putting a force on it from your hand. But once it's left your hand, now it's in free fall. So now it's only under the influence of Earth gravity. Anything that's in free fall only under the influence of Earth gravity. See, you can see from even the last last tables we looked at, it doesn't matter how fast it's traveling or in what direction it's traveling. Anything in free fall is always going to accelerate towards the earth at the same rate. It doesn't matter if it's going up, down, sideways, fast, slow. If it's only under the influence of gravity, it's always accelerating toward the earth. It's always picking up speed at the same rate. Okay, remember, this is not how fast it's going. This is the rate that's changing speed, okay, which has nothing to do with how fast it's going. Okay. So we're gonna throw the ball down. It's going this fast, but it's picking up speed at this rate. So after 1 second, now it's up to how fast? 30 meters per second. And after the next second. So it'd be like this all the way down, right? In fact, you know what? Isn't this like something that we just did yesterday, but you just start it from this row and just keep on going? Right? Like what if you took the second from yesterday's table and you define that as time 0? Doesn't that exactly turn into what we're doing right here? It's like the ball's already in motion. Okay, it's the same thing. Yeah, go.
Why is the velocity for 0 1 instead of 10?
Because I just made something up. I said you throw it that fast. So you can throw the ball at any speed. Okay. And I just made something up. I said, hey, let's say you throw it downwards at 20 meters per second. Okay. Okay. Yeah, so initial velocity can be any number. And for okay. So I guess here's the equation version of this. Okay. So this table right here, or this column with this table. Okay. It's kind of like using this middle equation. So I said, hey, suppose you threw the ball down at 20 meters per second. Okay. So and every passing second is going to pick up another 10 meters per second. Okay. So be 20, 30, 40, 50. Okay. So 10 times 1, 10 times 0, 10 times 1, 10 times 2, 10 times 3, okay, all plus the initial throwing speed gets you to these numbers. Okay. Is that right? Okay, is it? Okay, and well, let's do this. Let's knock out these graphs and we'll go back and worry about displacement later because that's the weird problem, right? So I wonder what this graph is going to look like. Okay. Can you guys probably envision what this graph is going to look like before I start plotting points? See it times 0, it's got 10, 20, 30, 40, 50, 60, 70, 0, 10, 20, that fast, 30, 40, 50. Let's go time 1, 2, 3, 4, 5 seconds. So at 1 second, now we're up to 30. After 2 seconds, we're up to 40. 3 seconds up to 50 meters per second. Then 60 meters per second, 70 meters per second. I see it's just going to be a straight line. That still with a slope of 10 meters per second per passing second. So it's called 10 meters per second squared. So that never changed. It doesn't matter how fast you throw the ball, which direction you throw the ball. Once the ball's left your hand, it picks up velocity towards the earth at 10 meters per second every passing second. Okay. How about acceleration versus time? What's that graph going to look like? Is that exactly like the last couple of A versus T graphs? Yeah, that's it. It's just 10 meters per second squared towards the earth. You define out as positive 10 meters per second squared. Okay, very good. All right, now let's go figure out the displacement values. Here, run the equations here. All right, so see, I threw the ball at 20 meters per second. 0 time has passed, 0 seconds, right? Plus 1/2 times 10 meters per second squared times 0 seconds being squared. What's 0 plus 0? 0. Okay, so at time 0, the ball starts at the cliff edge, which is also defined as position 0, just how we've defined it. Okay. All right, after 1 second, some paper I've been doing some math on. Here we go. Okay. After 1 second, so break out this equation. So x equals, I got 20 meters per second for 1 second, plus 1/2 10 meters per second squared, 1 second being squared. Okay. So that's 20 meters per second times seconds, that's meters. plus, well, this would all be 5 meters, wouldn't it? All right, 25 meters. Okay. So at 1 second, now it's 25 meters down the face of the cliff. Okay. See if you guys remember this from yesterday. If you had just dropped the ball, then how far would the ball have fallen in 1 second? You guys remember it was 5 meters if you just drop it? Okay, so now if you chuck it straight down instead, see it's way down compared to what it would have been if you just dropped it. Ooh, you guys see that, right? Okay. All right, let's do 2 seconds. So for 2 seconds, 20 meters per second times 2 seconds plus 1/2, 10 meters per second squared for 2 seconds being squared. Say that's 40 meters plus, see, 2 squared is 4 times 5 is 20. So we're looking at what, 60 meters? Right? Okay. 60. And you know what I'll do for these last three is I'm gonna do this in the calculator because this calculator has a pretty cool trick that I think I've shown you guys before or not, but I really like this model calculator. I'll show you guys one reason why. So V naught T, so that's 50 times, now we're at the 3rd second, 50 times 3 plus 1/2 times 10 meters per second squared times 3 seconds squared. Okay. That is 195. Now we're 195 meters. Okay. Now here's a cool trick with this calculator. Since I'm just changing out the time over and over, it's kind of like treating time as a variable, like independent variable. My dependent variables is displacement. In this calculator, you guys see above the negative key, it says ANS for answer. Okay. I'm gonna scroll up, scroll over, and in place of that 3 for 3 seconds, I'm gonna hit second answer. Okay. Then scroll to the right, and I see another 3 here. I'm gonna replace that with answer. Okay. Now, right now, this is junk. This doesn't mean anything. That's just silly. Okay. Well, watch what I can do. Hit the key 0, then hit enter. See where it says 0? Okay. Now scroll up twice. Scroll up, and it's going, oh no, this it's busted. Reset and reset. A little CPR on this. I think that should fix this. All right, so that was it. V naught times answer plus 1/2 times 10 times answer squared. Okay. All right, we're good. 0 equals. Yeah, okay, yeah, now it's working. Okay. So I scroll up twice, and now it's going to take that answer 0 and it's going to plug it in where the answer was. So 0, 0. Okay, so that 0 is that 0. Now if I plug in 1 for 1 second, hit enter. See, so now the calculator has stored the number 1. Okay. Scroll up twice, and now it's going to plug that 1 in where the answer is, which represents 1 second. So when I hit enter, what number should I get on my screen? 25 meters. Let's see if it works. 25. Hit 2, enter. Now the calculator is taking 2, something about 2, right? Scroll up, scroll up. It plugs in 2 for the time. Now what's it going to say? 60, 63, enter. Scroll up, scroll up. Now what's my calculator going to say? 195. Or what did they do?
Yeah, I got 105.
105. Did I mess up over here? I got on. Okay, should be 105. Oops. 105. Warning strikes again. How about 4 seconds?
160.
160. All right, and then 5 seconds. 225. All right. Okay, so that's how you can use a calculator, solve a bunch of very similar equations very quickly. All the way down. Okay. Now let's treat like XY coordinates. So X, or time can be 1, 2, 3, 4, 5 seconds. 0, 1, 2, 3, 4, 5. Okay. And displacement, well, the biggest one is 225, so we go like 100, 200, something like that. So we got 0, 0, 0 is a coordinate, 125, 260, 3, 105, 4, 160, and 5, 225. Okay. Now, that is is that still parabola? Yeah, but it looks kind of like a real shallow parabola, doesn't it? Kind of like a real shallow parabola. Okay. Which is true. And I want to contrast that one with the last couple that we did. You guys remember if you just dropped the ball, the vertex was right at the origin point. Nice vertex right there. Get like half a parabola. And then if you throw the ball upwards, then there's very clearly a parabola with the vertex way down here. Where do you guys think the vertex would be for like throwing the ball downward? If you completed the parabola, do you think it'd be like in negative space out? Like, do you think the rest of the parabola would look something like this? And the vertex would be like way the heck down here. You guys think? You guys see that? So this is like like way off on the arm of a parabola, isn't it? Like way off on a wing. You guys that too? All right. Let's do. You guys ready to move on? Next example. Okay. Let's do a car braking to a stop. Now a car braking to a stop. Find let's think about this. Shouldn't that be like moving forward? But which way is the acceleration? Negative, right? So positive velocity, negative acceleration. Like the car is moving forward, but slowly to a stop. Okay, so we're about to do an example that involves this quadrant. Okay. And here's two where okay. There's a point that I probably should have made by this point in the class. A difference between velocity and acceleration. Right? So suppose you're yeah, thank you. Suppose you are in a car. Maybe you're a passenger and you're blindfolded, and your friend's driving the car, and you're going up I-95. Can you feel whether that car is going 50 or 60 or 70 miles an hour? If you're blindfolded as a passenger, let's say you just cruise control, constant velocity. Can you feel the difference in speeds?
No.
You are correct. You cannot feel the difference in velocities. Oh, that's interesting. This, by the way, all velocities are relative. This is going to be a setup for relativity. I'll eventually tell you about one day, probably in spring. So, but you can feel something in the car, right? What are the three main controls you have in the car that you can actually feel?
Brake.
Yeah, you can definitely feel the brake. What else can you feel?
So
Yeah, if you slam on the gas pedal and you're actually like speeding up, moving forward, acceleration, you can feel that, right? There is one more. It's a little trickier to think about. What's the third thing you can feel? Turning. Steering wheel, right? Okay. Now that one we're going to say for unit 3, right? If you're going around a curve, so there's a type of acceleration you can calculate with that called centrifugal acceleration. We're going to put that one to the side for now and just focus on just linear motion, just forward backward. But yeah, anything you can feel in a car is not its velocity; it's some kind of acceleration. You guys get that? Okay. And what causes an acceleration is a force. Okay, so that's a Newton's law of motion we'll look at too. So it's a force that causes things to accelerate, to speed up, to slow down, and that's what you can feel. So you don't feel velocities; you only ever feel acceleration. Okay, so let's do that. Let's do an example: car brakes to a stop. Car brakes to a stop. Now, okay, what question am I going to ask about this? I mean, I can ask a bunch of questions, right? Maybe I want to know how far did the car go? And so there's our scenario. Okay, here's the question: how far is the let's say braking distance? Braking distance. Maybe you're driving your car, la di da, and then you see something in the road in front of you, you're like screech on the brakes. Like, okay, well the car's still gonna move forward some distance. Are you gonna slam into whatever you brake for? Well, fair enough. We do some physics and do a calculation and find out, right? So you're gonna have to have some information. Maybe you want to know like how fast is the car going? Okay, so here, let's do this. I'm trying to introduce an idea to you guys that there's only here. How many different variables do you guys see floating around here? How many different ones? Yeah, 5. There are 5 different ones, right? I see time. I'm gonna put time down here. You could possibly be speeding up or slowing down. If you are, that would be acceleration. There could be some kind of displacement x. There could be an initial velocity and a final velocity. Initial velocity, final velocity. Okay, so if you keep it track, okay, that's it. There's only 5 variables that we're jumping around. Okay, now you might say, well, aren't there like a million different velocities car braking to stop or drop a ball off a cliff? There are like a million different velocities, which is true, but in the equations, all you really care about is what's going on at the very beginning, what's going on at the very end. Here's the displacement from beginning to end. Here's the time interval. Right? Guys get that? Okay. So there's only those 5. Now, if you want to answer the question, what's the braking distance? Which one of these are you solving for? Maybe x in meters, right? Like how many meters? So we're solving for that. So you have to know some of these other things. If you're braking to a stop, you actually know already one of those other things. What's one that you already know?
The final velocity.
Final velocity, exactly, right? And so that has to be what number? 0 meters per second. Good call. Okay. So when you're solving problems and you're eyes are around, you're looking for numbers. Okay, I need numbers to feed into equations. There might be some hidden numbers like that. You have to say, hey, I know. Brakes to stop means final velocity 0 meters per second. So I have a number. Okay. But that's not enough to solve this. You have to know something else. What's something else that you might have to know?
How fast we're initially going to go.
Hey, how fast you were going initially? That might be good to know, right? Okay. Now, if you just know that, if you just know how fast you're initially going and the fact that you're braking to stop, let's say you just have those 2 numbers. Would you have enough information at that point? Here, I'll make up a number. Let's go. Let's call it 30 meters per second. Okay. Is that right there enough to answer that question? Do you guys think? You guys are saying no? Huh. Okay, so maybe some of you guys are saying no, that's not enough. Maybe you're not sure. Okay, if you weren't sure, let's see, you're solving for x and you have the 2 velocities, right? You have the 2 velocity. Ooh, 2 velocities, solve for x. I would still need to know the rate that their car is slowing down, right? Or what if you did 2 velocities and solve for time? Okay, well, you still wouldn't know that. Yeah, there is not enough information to solve this at this point. Okay? Now, there's a general rule for solving any linear motion problem. Guess how many total pieces of information you need to have to solve any linear motion problem? 3. You need 3. There's only 2 on the board here, so you need something else. You either need to know how many seconds it took for the car to brake to stop, or the rate that the car can slow down. You guys think the rate the car can slow down has something to do with like the material properties of the tire and the asphalt? Okay. So I'll go ahead and give you guys that one. Let's say this number is like I'm gonna call it -10 meters per second squared, which is pretty realistic if you have new tires and it's a dry road. So if it's been raining outside, do you think that number would have a magnitude that's closer to 0 or a larger magnitude? What do you guys think?
Closer to 0.
Closer to 0, right? Okay, so if it's been raining outside, it might be close to like -5 meters per second squared, and it takes a long time for our brake to stop. Okay, so at this point, now there's enough information to solve this problem. Let's get a picture going. Car initial velocity is 30 meters per second. There's going to be some braking distance, x, where final velocity is 0 meters per second. Okay, so we got a picture, got some numbers. Okay. Now, which equation, the first, second, or third, is going to solve it for you? Okay. I'm hearing different candidates. I'm hearing the second and the third. You guys are saying, right? I'm gonna. You could actually solve it multiple ways. The most direct way to solve it would be the third. Yeah, would be the third one. Notice which variable is not listed in the third one. Time. And notice how I did not give you time and I'm also not asking for time. That's usually an indication that the third equation is the fastest way to solve it. So let's do it that way first. Let's go final velocity squared equals initial velocity squared plus 2ax. Okay. Then we'll go back and we'll solve it another way if you like another equation. I'll show you guys that it'll be the same thing no matter how you solve it. Okay. Now I told you guys this one you could get from a system of equations. If you're really curious, that might be a good thing to do is like go home and actually work out the system of equations of the top 2 and actually prove that this is true. Okay. But I'll sort of prove it from a backward point of view. I'll show you guys that you get the same number for stopping distance no matter how you solve it. Okay. So let's plug in 0 meters per second here, and that's being squared, is equal to 30 meters per second here, also being squared, plus 2 times -10 meters per second squared times the stopping distance that we're solving for. Okay. Oh, before I get plugged in and chugging too far, I do want to point out a weird thing about this third formula. Guys, whenever you square a number, suppose one of these velocities was negative, would you lose that information by squaring it? Yeah, because anytime you square something, you lose the negative information. Every rare once in a while, that'll run you into trouble. So just kind of be aware of that in the back of your mind. That's a really rare thing to happen, but just in case you run into that. Okay, so looks like a couple of algebra steps to get to the answer. I should subtract over this 900. Right, so -900 meters squared per second squared, and then divide down this -20 meters per second squared. Okay. Now all the units cancel except for meters. Right? Meters squared per second squared divided by meters per second squared. Doesn't that give you meters? The negatives cancel, the zeros cancel, and what's the answer? 45 meters. There you go. X is 45 meters. Okay. Just for scale here, let me Google this real fast. I should know this, but okay. Oh, come on here. Google 30 meters per second to miles per hour. That's about 67 miles an hour. Okay, so that's definitely highway speed, right? Right, 67 miles an hour. Right. Oh, you know what I want to point out, and this will definitely come back in a big way in Unit 4 when we do conservation of energy, because there's another way to solve this problem with conservation of energy. Okay. What if you had doubled your speed from 30 to 60 meters per second, 30 to 60 meters per second? What would happen to your braking distance? And it doesn't also double. Okay. Guys, if you throw a factor of 2 on this initial velocity, what happens to that factor of 2? Gets squared. Isn't that like 4 times the whatever? Right? And if you divide that, you're going to slow down at the same rate. You have the same tires on your car. So twice the initial speed translates to how many times the braking distance? 4 times. Whoa. What if you had 3 times the initial speed? What? 9 times the braking distance. Guys, that? So hold on to that in the back of your mind. Let's come back to Unit 4. But I want to tell this a different way. Because some of you guys said, hey, what if you use the second equation? And you could do that. But if you use the second equation, you see how with what I gave you, you'd actually solve for time? Well, because that would give you braking time, and then you can take that braking time, plug into the first equation, and get x. Which, if you do that way, you think you should still get 45 meters? Let's try it out. Let's see if that works that way. So let's go final velocity equals initial velocity plus acceleration times time. Okay, let's start popping stuff in here. So I know I'm going to 0 meters per second from 30 meters per second, and then slow down at a rate of 10 meters per second per passing second for some amount of time. You say we subtract 30, divide by -10, so it's -30 meters per second divided by -10 seconds. Or sorry, meters per second squared. Oops, meters per second squared is the number of seconds. Do you guys see it's going to be 3 seconds? Great. Okay. So we have a 3-second braking time for this particular scenario. Is that okay? Great. And once you have that, now can you go back equation shopping and plug that into the top equation and get stopping distance? Okay. And you guys know what the answer is going to be already. What's the answer again? 45 meters. You guys think we're going to get 45 meters? Moment of truth. See if this doesn't work. Displacement equals initial velocity times time plus 1/2 AT squared. So we're doing initial velocity was 30 meters per second. Now you guys know the braking time is 3 seconds. So I can pop that in. Plus 1/2 times -10 meters per second squared times, okay, here's 3 seconds again, but this one's being squared. Okay, the square only applies to the time. Okay. So that gives you, it's like 90 meters plus 3 squared is 9 times -10 is -90 divided by 2, it's -45. That's meters. What's 90 minus 45? 45. It's the same thing. Look at that. There's two approaches. It's the same answer. Okay. All right, you guys all right? Okay, who's got any questions so far? Question. All right, so that is the main chunk of notes that definitely wanted to do. We have about an hour, which is awesome. Okay, we have about an hour here. Okay, okay. So since you guys are in groups, I do want to set you guys up with some teamwork pretty soon. So let's do this. I gave you guys a couple of pages. One is the college physics problems, but the other one is, you guys remember this page? Okay, has a table of values on one side and conceptual questions on the other side. You guys remember this? Okay, let's take a look at this, the side with the tables on it. Okay, so hey, look, it's a bunch of taxvv tables: time, acceleration, displacement, initial final velocity. Right now, this is you won't really see this in any textbooks, but this is just a framework I've come up with to help students over the years. It's like, hey, how do you really solve these problems? Right, and you guys sort of told me already. You said, well, you figured out you really have to have three pieces of information to solve any one of these problems, right? So if you big picture, look at the tables here. There's every combination of three variables that you could have. Like the number one, you see acceleration, displacement, initial velocity, right? Or number two, t, a, and x, right? So any combination of three that you can think of is somewhere on this paper. Is that? Okay. And there's a pair of questions per scenario, because each one of these tables is a scenario, right? I give you a little story that this might apply to. Okay? There's a pair of questions. And the pair of questions, oh, well, that's the other two variables that you could possibly be asked to solve for. You guys see that? Okay. Now, every one of these is an accelerating example, except for the first scenario, because I wanted to give you guys at least one non-accelerating. Right? Although, guys, if it's not accelerating, doesn't that just always boil down to that equation every time? X equals vt. Because if the acceleration is 0, boink. Okay. And then for this one, velocity doesn't change. This one, velocity doesn't change. Okay. Okay. So, which is kind of boring, but I mean, you have to know this equals speed times time. Okay. Okay. So let's do that one, and then I'll pick out a couple of ones with you guys, and then I'll let you guys work in teams, right, for some practice here. Okay. So the first scenario, remember this is the only constant velocity one that I gave you guys. A baseball thrown from the pitcher's mound travels to the plate at approximately constant velocity, right? I mean, it'll accelerate a little bit, but ignoring that, right? Doing an approximation here. Calculate the batter's reaction time and the final velocity crossing the plate. If you know the pitching speed, that's what V naught is, right? Initial velocity, that's their pitching speed. And 18.4 meters, that is the distance from the mound to the plate, which is actually defined as 60 feet 6 inches, which is probably a handwriting typo. It's probably, saw somewhere on the internet where everything is true that it's probably supposed to be initially 60 feet, but probably somebody had sloppy handwriting and not 60 feet 6 inches. We're going to use metric, 18.4 meters. So this just very simply is displacement equals velocity times time, or if you like, you say velocity is displacement per time. And first question is, what's the batter's reaction time? Given the distance from the mound to the plate is 18.4 meters, and the pitching speed is, well, my paper says 41 meters per second. Now, there's lots of versions of this paper floating around, so you guys probably have a different pitcher with a different pitching speed, right? Or if you're lucky, maybe you have my pitcher with my pitching speed. And then how much time? Okay. Can you guys solve for time? And take that distance in meters, divide by the speed in meters per second. The meters cancel. The seconds is going to flip back up on top to describe a time. Okay, let's see how the numbers play out. That divided by that. Okay, that is this many seconds is the time. Time is that many seconds. There you go. Okay. And the faster that the pitcher pitches the ball, the less reaction time. You guys see there's an inverse relationship between throwing speed and reaction time? Is that? If you make one bigger, the other gets smaller. Oh, yeah.
43 because the velocity is 43.
Ah, yeah. So if you change the pitching speed to, let me just scroll up, scroll over. Okay. So if I increase the pitching speed all the way up to 43, ooh, you're right, the reaction time goes down. Yeah. right? So inverse relationship. Okay. You guys get it? Okay. Now, the other question is, what's the speed that the ball crosses the plate? Well, if there is no acceleration, then isn't final velocity just equal to initial velocity? Okay. And if you really want to see that spelled out in the equations, you okay? Okay. So, whoa, what's wrong here? Okay, let's get it. Let's see. Okay. I bet you could use, how about that second equation, right? Just to kind of overkill here. Final velocity equals initial velocity plus AT. But if acceleration is just 0 meters per second squared, this bit goes away. Okay, and then the throwing speed is the speed that it crosses the plate, as long as it's not speeding up or slowing down. Okay, that'd be true. So do you guys have number 1, number 2 finished? Okay. We pick another couple scenarios here. How about I'm gonna do number 5, 6, 7, and 8 with you guys, and then I'll let you guys work in teams, help each other out. Okay, so let me model this for you. Okay, number 5. So 5 and 6 go together, right? You guys see a ball. Never mind. Let's do. Yeah. Okay, let's do that. Let's do it. Okay. Ball dropped from a treehouse, reaches ground at a given time. Some of these other examples have you like throwing the ball, but this one we're just going to drop it, which is pretty straightforward, right? Find the height of the treehouse and the speed that the ball hits the ground. Oh, it looks like I used 9.8 meters per second squared. Right, so that's just more precise value for Earth gravity, right? Oh, it looks like there's a 1 second, or it gave you how much time it took to reach the ground. My paper says 1 second. Right? And the fact that the ball is dropped, maybe I should not have explicitly given you initial velocity, but you would know, you would be able to figure that out, right? That this would be 0 because of the word dropped, right? You guys can figure that out? Yeah, so we need to figure out 2 things. What's the height of the treehouse, and how fast is it crash landing? So height of the treehouse, is that the first equation? Okay. In fact, if you just drop it, release it from rest, what happens to this term right here? Just goes to 0, right? Because beyond would be 0 if you just drop it. So isn't it just 1/2 AT squared? Okay. Okay. Hey, is that? You guys remember Paul Hewitt a few minutes back? Dropped something in mine shaft. It fell for 5 seconds. I wonder how deep it is. It's about 125 meters deep. College. You guys remember that? A few minutes back. That is that, isn't it? So we're just gonna do that, but for a treehouse. So number 5 and 6. Okay, I'm gonna draw you guys a picture. Probably good practice to draw pictures for these too. Or I don't know. I like pictures. So I wonder what is that distance x? Sometimes you call it y for vertical, especially when we get to projectiles, or we might say h for height. Okay, I'm gonna take a ball. Say v naught is 0 meters per second. Ellisted gravity is more precisely 9.8 meters per second squared. It looks like on this page, so we'll just run with that on this page. And I also know the time. So t equals, and my page says this many seconds, right? So let's do how far is it falling? X equals, I'll just use the boiled down version of this, 1/2 AT squared. Okay. So that's going to go 1/2, go 9.8 meters per second squared. And then I'll let it fall for 1 second and square the time. Okay. Is that going to be this many meters? Okay. Which is actually something that you have in your notes from yesterday. I've got a ton of papers here, but so we dig this up real fast. Here it is. Here it is. So here's your yesterday notes. Ball, edge of cliff, drop. After 1 second, it would have 5 meters. Aha, look at that. You guys know that? Okay. And the other question is, how fast is it crash landing? So velocity equals, well, v naught plus AT, but I'll just boil this down to, thank you, simplified version. It picks up 10 meters per second every passing second. Does that for this many seconds. Oh, that's this many meters per second. Or whoops, I forgot to use 9.8 on this page, but you guys get the idea, right? Okay. You guys get that? If I plugged in 9.8, it would just be 9.8 meters per second. Okay. Any questions on 5 and 6? Okay. next scenario, number 7, number 8. A ball is dropped off a cliff of given height. Okay, so we have a cliff of this height right here. Oh, ooh, on an alien planet. Ooh, spooky. So if I'm throwing an alien planet at you guys, what do you think variable is going to be special? The acceleration. Ah, that's one thing I'm going to have you solve for. It takes this given time for the ball to reach the ground. Find the gravity field of the planet and also the speed that the ball is crashing onto the ground. Okay, so we got a cliff of known height. Maybe like drop a rope and measure the rope, or somehow measure the height of the cliff. And also, we got a pair of astronaut buddies, and one guy's dropping the ball, and the other guy's it measures the amount of time to reach the ground. Okay. And also drop from rest. That's 3 pieces of info. So let's do the number 7 and 8. So same as before, I'm going to draw a picture and label what I know. We'll go from there. Got a cliff. I know the height of this cliff. So I'll say, I'll keep calling it X. So you might see Y or H. And my cliff is, you know what? Dude, here's what I'm gonna do. I'm just gonna call it X. Okay. I'm gonna solve this one in terms of variables, which is a good practice to be able to do, especially in AP. I'm gonna have you guys solve it in terms of variables sometimes. What if it's any cliff on any planet, right? Could you come up with like some algorithm that you could just like plug into a calculator Excel page? It's like I can solve anything. Okay. So got this astronaut guy up here dropping this ball, and I've got this astronaut down here brought a stopwatch with him, and I know how much time t. Let me make this really generic. I'm going to say this guy throws this down at some speed, some initial velocity v naught. Okay. That could be 0 if you drop it, but I'm going to make it even more general, okay, which might probably solve one of the other scenarios on this page. Okay. So I have these 3. I know v naught, I know x, and I know t. Okay. I have a little table up here in case this helps. So check, check, check. And we're solving for what's the gravity of the alien planet. And also, what's the crash speed? Here, by the time this ball gets down to the ground here, to have some v final. I'd like to know that. And I'd like to know what's the gravity field of the planet. Okay. All right, and we're going to solve this whole thing in terms of variables. No, there's no numbers on this, right? No numbers. No numbers. I'm going to solve it for everybody right here. Or we'll do it together. All right, so you have t, x, and v naught. Which formula looks like a good place to start? First, second, or third? You guys like the first one? I like the first one also, because we have everything except for that A, which is the gravity field of the planet, right? So we did it. Let's do that. So the height of the cliff equals the throwing velocity times the time to reach the ground plus 1/2 times the it's okay if I turn A into G. Is that okay? G for gravity field. Sometimes you see that. Okay. I'm going to solve for what is that gravity field given everything else. Is that okay? Okay. Now, before I get going too far on this, notice the way I drew the pictures. I have the guy kind of chucking the ball downward. What if he threw the ball upward? Do you think that this could eventually solve for that scenario also? You could just plug in a negative value for v naught. Yeah, that would also work. Okay. So yeah, v naught could be anything. Up, down, fast, low, drop. Okay. We're gonna solve for g. Can you guys solve for g in terms of variables? Give you guys a head start. See if you guys can beat me to the answer. Can you guys solve for g given everything else? I hope you're beating me to the answer. Did you guys get that? So what you guys got? You guys beat me to that, right? right? It's just algebra, just with variables instead of numbers, right? Just same algebra process that we reviewed a few days back, and that you guys probably knew before you even walked through this class. You guys can do some algebra, right? Okay. Now I want to see if my numbers, if I can actually plug them in and get one of the answer choices. So is this actually going to work? Oh, right before I do that. Okay. Do you guys see I have a subtraction here? Remember, you can only add or subtract things that have the same unit. What's x measured in? Meters. What is meters per second times seconds? Meters. So it's okay if I subtract those two? Yeah, it's meters minus meters. You guess that? All right, let's try this out. Let's go 2 times, open parenthesis. The height of my cliff was 30 meters. Okay, subtract now my throwing speed happened to be 0 because I said drop ball. So 0 times the fall time of 5 seconds. Okay. All divided by the fall time squared. That's 5 seconds being squared. Okay. So the number on my screen should tell me what the gravity field of the planet is. I'm getting 2.4. What unit goes with that? That's 2.4 what? Meters per second squared, because it's a gravity field. Right? Or if you like, the numerator's in meters, the denominator is definitely in square seconds. That's meters per second squared, isn't it? Ah, okay. And that is an answer choice. So there you go. Got that. Or at least on my paper, it's an answer choice. Okay. Are you guys also getting an answer choice on your paper for your numbers? Okay. There's a follow-up question. So let's do this one, and then I'll let you guys work in teams. Get real close here. Got to wrap this one up. The other question is, what is the crash speed as it's crash landing down here? Okay. Which equation you guys build using the crash speed for second or third?
Second.
I like the second one also. Okay. Now, if you said the third, you could definitely use the third, but I agree with you. Let's go with the second one. That looks a bit more straightforward. Let's do that. Okay. So the crash velocity is equal to the initial velocity plus, well, let's say GT. Sure. Okay. And say I gave you initial velocity. It really is just 0, but okay, got that. I gave you the time and this gravity field. Well, that's this whole expression right here, isn't it? Isn't this gravity field? This whole expression 2 x minus b naught t all divided by t squared. Or maybe you cleaned it up and wrote slightly differently than that. That was it. So final velocity, like crash velocity, is initial velocity plus 2 times the height of the cliff minus throwing velocity times fall time over fall time squared times the fall time. Oh, well, isn't one of these just going to cancel out? One of these t? So clean this up a little bit. Crash velocity equals initial velocity plus 2. Let me do this too. I'm going to go ahead and expand this out. Can you distribute this 2? Is that okay? It'd be like 2x over t minus 2 v naught t over t. Is that okay? Okay. And do those t's cancel? Great. You see it? Oh, and what's v naught minus 2 v naught? Negative v naught. So final velocity equals negative initial velocity plus 2x over t. Okay. Another way is saying that, hey, what do you guys just think this is? Plain x over t, the cliff height over the fall time. There's a name for that that we hardly ever talk about in this class. You guys remember v bar from earlier in this class, which stands for what? Average velocity. Average velocity. So if you have twice the average velocity and you subtract the initial velocity, that should give you the crash velocity. Right? Here. Let's do this. Let's plug in the numbers, make sure that that works with an answer choice. And then I want to show you guys graphically why this expression is true. I'll show you guys graphically why this is true. So let's try the numbers. So this is number 8. So, well, negative v naught is just 0 because they drop. So it would just be twice the average velocity. When 2 times the cliff height divided by the fall time, I'm getting 12 meters per second, and that is a number on my paper, that's the choice, so that looks good. Okay, so this works. Okay, now why does this work? Why does that expression work graphically? Show you three scenarios why it works graphically. Because you could drop the ball, or you could throw it up, or you could throw it down. Okay, so let's go drop the ball, throw upward, and throw downward. I'll define down as the positive direction, just like I have been all day today and yesterday. Okay. So let's do a bunch of V versus T's. V versus T, V versus T graphs. Okay. Now, if you drop it, is it going to look like just like that? Here's your initial velocity. Here's your final velocity. Okay. Now, what does that have to do with? Okay. Do you guys think that average velocity? Where do you guys think average velocity would be on this graph if you just drop it? You guys think it'd be like right there? Okay. In fact, do you guys think that average velocity would be the area of this triangle, which is distance, divided by this time? Hey, could you guys imagine if this, do you guys get a triangle right here, physical triangle, which represents displacement? Can you make that out of ice? Can you guys imagine it have a giant ice triangle? And I put some aquarium walls and I let it melt, and it melts down to this dash line right here, because it's going to melt down like that, right? And this here rectangle has the same area as that triangle. Okay. And this right here is V bar. Okay. Now, that matches up exactly with this formula, because look at that. V not zero because you dropped it. Right? You guys see 2 times average velocity. This right here, x over t, is average velocity, isn't it? Ah, you guys see how the final velocity is twice the average velocity, according to both this graph and this equation? Right? You guys see that? Because, okay, let me change colors here. This x over t, that is V bar. That's your V bar. So 2 times the average velocity is the final velocity if you drop it. Okay. What if you throw the ball upward? That means you're throwing it in the direction that it's also accelerating, which should just make it look like this. Here's your V naught. Here's your V final. Here's your V bar. Right, so this time you have a trapezoid made out of ice. Let it melt. It's going to melt down to that dash value. Here's your V bar. Okay. You guys see how final velocity would be your average velocity plus, or sorry, what is it? Here, how's it go? So two times the average velocity. So take this average velocity, double that looks like this tall, and then subtract off the initial velocity. Here's your initial velocity. So take twice the average, subtract the initial, bring it down exactly to the final velocity. Okay. This is kind of a weird way of thinking that works. Right? And then finally, what if you throw the ball? I messed these up, didn't I? Hold on, throw the ball. Sorry, this one should. Another boring mistake. So here's downward. Change the scenarios. Downward. Okay. So here's going to be upward. Which I had the axes set for, but okay. Oops. Sorry about that. If you were a step ahead of me, then your graphs might be okay. You guys get that? So now here's your initial velocity. Here's your final velocity. And average would be like halfway between those, which is like probably right about there. Here's your V bar. Is that? Okay. And then how's this match up? Okay, so if you do twice that average velocity, so here's average velocity. If you double that, it brings you up to about here. And then you subtract initial velocity. Now, guys, if you subtract a negative number, is that the same thing as adding it? So if I take this value and I tag that on right here, oh, that brings me up exactly to final velocity. Okay. So there's the graph versions of this general equation. Okay. Here, good. Who has any questions right now? Any questions? Yeah, go.
So on number 3 and 4, how do you find the initial velocity without the final velocity?
How do you? Okay, so number 3 and 4, I did not give you either one of those velocities. So if I don't give you either velocity, okay, kind of hard to use this one because you can't solve this by itself. 2 unknowns. Can't use the last one because there are 2 unknowns. So if you just want to use one equation, you can't have 2 unknowns and solve it. Okay. Could you use the top equation and solve for V naught? You could do that, right? You guys think number 3 and number 4, you have enough information you could solve for initial velocity given everything else? And then once you have initial velocity, do you think you could go ahead and also use one of these other equations to solve for final velocity? Right? That could be a roadmap, right? Okay. All right, so, all right, this worked out pretty good because we have a solid, what, half hour in here? Ooh, over a half hour. Okay, we have over a half hour. So here's what we'll do. I'm gonna give you guys the rest of the class time to work with each other, solve as many problems as you can with each other. Here's let me give you guys some pointers here how to do this. Obviously you can solve numerically. Even better if you can solve in terms of variables. And it's also a good idea. You guys are just gonna craft your own notes with each other, help each other out for the rest of the class. And I'll walk around and help you guys out too. If you can also draw pictures for each scenario, right? So draw a picture. If you can solve in terms of variables, that'll give you a huge head start in this class. If you can solve numerically, that's good too. But if you solve in terms of variables, then you can just solve everybody's all at once, right? You guys get that? Okay. And so go ahead, knock these out. Probably a good idea to, if you have extra time too, to take a look at these conceptual questions on the other side, which we'll probably eventually do before in this class too. Okay. So you guys got the rest of the class to knock those out. I will walk around and help you guys out.